So this is a lesson on water and carbon cycles. We're looking at section 3 of the water and carbon cycles, Earth life support systems, which is how much change occurs over time in the water and carbon cycles. At times during this video there'll be activities to do that you can do on paper, or if you want to you can sort of open the PowerPoint and do it in there, or however. So what I suggest is if you just pause the video at those points and you can complete those, and then I'll kind of carry on, and when you press play you'll be able to sort of find out what the answers are and things like that. So to start us off, this is a bit of a recap of an early part of the topic. So we've got a diagram of a drainage basin, and there's some yellow boxes that need completing to show what's going on here. So it's largely storage and some flows of water. So have a go at figuring out what goes in the yellow boxes. So here we are, we've got answers. So when water lands in a tree, it's called interception, which is a type of storage. It then can go down to the surface in surface storage, and then we've got soil moisture, groundwater, and we've got a few movements of things like through flow, and we've also got the output of transpiration. So hopefully terms that we're remembering from previous lessons, and it's just a bit of a recap. Okay, so like I say, change in the water and carbon cycles, so primarily looking at what causes these changes, and part of the evaluation of this will be thinking about what has the biggest change, and what kind of causes change over a long period of time, or causes quite an immediate change over a short period of time. These are the sorts of ways that you would be assessed on this. So just to start us off, we're going to look at ideas like dynamic equilibrium in the water and carbon cycles, and a little bit to do with feedback loops. So just a bit of a reminder about this, that basically the reason we're looking at this is that feedback loops come up a lot in Earth life support systems, and it's a really key idea to understand. So hopefully we remember that a positive feedback loop is a situation in which a change happens in the system, and that change creates more change. So we looked at this with glaciers. So the idea that if the glacier begins to melt, then the valley has less reflective surface in it, and therefore there'll be more rock, which is more absorbent of the sun's energy, and this means the glacier will melt even more, and it will keep going and keep going. Whereas negative feedback is where change is reversed and it goes back to normal. So the way we can visualize this is with a graph. So lovely graph. So we've got time along the bottom and amount of change up the side. So the way that I would generally visualize this is negative feedback loop looks a bit like this. So something begins to change as it goes up, and then it will come down again as something negates that change or cancels that change out. Whereas positive feedback loop is increasing in either extreme. So either the planet, for example, getting warmer and warmer and warmer, or colder and colder and colder, due to change creating more change. And the graph looks a little bit like something like a crocodile with its mouth open and a tongue, or a snake maybe. So that's sort of a way you can remember what the graph looks like, and it's a good way of visualizing the way these work. So we'll have a look at a couple of examples. So as it says, negative feedback loop maintains balance within the system, and dynamic equilibrium is that balance. It's that thing staying broadly the same. This is discussed on page 120 in the textbook if you want a bit of a look. So got a couple of examples here. So in the drainage basin, if we get very heavy rainfall, we will get an increase in water in the aquifers. This will lead to a rise in the water table, an increased flow out of springs, so there will be more discharge in the river, and the water table will return to normal. So the system has reacted to the change naturally, an automatic reaction, and this has brought things back into normal alignment. Okay, so that's an example of a negative feedback loop. We have another one here. So this is a carbon cycle. So we burn fossil fuels. This increases the amount of CO2 in the atmosphere. So what you want to think about for a negative feedback loop is what could happen to the CO2 in the atmosphere that would remove it, which would bring it back to normal. So what kind of natural processes can kick in and return life to normal. So essentially, if all humans stopped burning fossil fuels and then we just started living very green eco-existence, the amount of CO2 in the atmosphere wouldn't just remain there, something would happen to it, a feedback loop would kick in. So if it were a negative feedback loop, then what we would see is an increase in levels of photosynthesis from plants. So there's more CO2 available, plants can photosynthesize more, and then this will remove CO2 from the atmosphere. So ultimately, this is the kind of long-term negative feedback loop, which will happen on the planet, which will bring things back into alignment. There's a range of positive feedback loops that could also happen that would result in more and more CO2 going into the atmosphere, and it sort of just depends on a range of factors as to why one would happen and not the other. So I want you to have a go at putting together some positive and negative feedback loops. So on the next slide, which I'll show you in a moment, there'll be 7 different cards or phrases, and these go together to create both a positive and a negative feedback loop. So what that means is you will essentially start off with a single starting point. It will then go, just to give you a clue, to another card, and then you'll basically get a couple of loops coming off like this with various statements on them. Okay, so that's sort of roughly what we're looking to create. So the first card is global temperatures increase, so that goes here. So what you need to look at when we go to the next slide is what will global temperature increase directly lead to, and then that goes in the next card. And then this should lead to a positive feedback loop and a negative feedback loop. So you should have a couple of cards that go on the positive feedback loop and a few cards, I think it's 3 cards, that go on the negative feedback loop, and that should be the general arrangement that you're looking at. Okay, so what the idea here is that the same starting point, the same input of global temperatures increase can lead to 2 different outcomes, a positive feedback loop or a negative feedback loop. So we'll have a look at the next slide. So these are the statements. As I say, you're starting here with global temperatures increase, and you need to figure out what does that then lead to and how does that create a couple of feedback loops. So I'll just give you some time. I'll say pause here and try and figure out what these 2 feedback loops are, and then we'll go on to the next slide. Okay, so as I say, starting with global temperatures rise, that then leads to, and if you're struggling, you can take these a step at a time, keep pausing and sort of giving yourself clues. That leads to evaporation increasing. So more temperature, you're going to get more evaporation. That will then lead to the atmosphere holding more water vapour, and water vapour is a greenhouse gas, so that has created a loop which is leading to even more warming, because water vapour is a greenhouse gas that will absorb even more heat. Or evaporation increase will lead to increased cloud cover, which will lead to more solar radiation being reflected, and this will lead to a global temperature fall. So you need to figure out which of these is positive and which is negative. So which one is leading to more change and which one is leading to a reversal or a cancelling out. So this one on the left is the negative feedback loop. It's cancelling out, whereas the positive feedback loop is getting more and more extreme. So this one on the left, you can actually kind of keep adding points, if you like, so that it goes all the way back to global temperatures rise. So global temperatures fall would lead to evaporation decreasing, would lead to decreased cloud cover, and that would therefore lead to less solar radiation being reflected, and then so global temperatures would rise. So you can actually bring these green arrows around, so they form quite a large loop, but it'll go all the way around to the beginning again, same as the positive feedback loop, but it basically just it just means reversing a lot of the terms that already exist. Okay, so this section we're looking at how humans cause changes, first of all in the water cycle, and we'll look at the carbon cycle as well. So what do humans do that cause these changes? So first of all here we are looking at urbanisation having occurred, so people having built a city. So on the left here we have a rural area, and we've got the various percentages of what happens to water and its movement, and then on the right we have a city with impenetrable surfaces. So the key difference you can see here, the big thing, is that runoff on the right is at 55%, whereas on the left it is 10%. So evapotranspiration doesn't vary enormously. We've got a slight change, but the big thing here is a massive increase, so 5.5 times more runoff. So you've got to think, what's the impact of that? What does that what happens to the water cycle with that? Well, ultimately we're going to be looking at an awful lot more flooding, and therefore a lot more risk downstream to people and property, etc., that are down there. So you generally find that the rivers that experience large amounts of flood in the UK are the ones that travel through a lot of urban areas. So we find that with the River Severn, which starts in Wales and it travels through lots of cities in the west of England, so places like Worcester and Gloucester, and there was a lot of issues this year with flooding there. And it's because there's so much runoff from the land, and it flows all into that river, and it creates a much higher peak discharge, and we'll sort of look at that shortly. So that's urbanisation. So there's a few notes here on this you can jot down. So when we sort of urbanise an area, we're turning rural land into urban land. Often this results in building on floodplains as well, and this will increase the river flow. So when we increase the amount of tarmac and concrete and impenetrable surfaces, we decrease infiltration and we reduce the amount of water being stored on the ground surface, and we massively increase sort of surface flow. So water just flows rapidly into drains and into the sewers and then out to rivers. Whereas if you sort of look at heavy rainfall in the countryside, then you'll often see fields becoming waterlogged and having lots of surface water, and that's really good for preventing flooding because all that water is being stored in the fields rather than being rushing off into the countryside or into the rivers, sorry. So we can look at this in this form. This is a storm hydrograph. So these aren't specifically covered within our course, but they're a really useful way of visualising what's going on. So the bars here are rainfall. So that's rainfall in millimetres, and we've got that here on the y-axis. And then we've also got this line coming up, and this is runoff in cumecs. So a cumec is a cubic metre of water per second in a river. So this river is coming up to 50 cubic metres of water per second, coming all the way up from its usual flow, which is down here below 10 somewhere. Okay, so the river, this line here represents how much water is in the river. So this is the discharge of the river, and you can see it's rising really rapidly, and then up here is the peak flow, the peak discharge, and we've also here got what's called the lag time. So this lag time is the time between the peak precipitation, the highest level of precipitation, and the peak discharge. So this river has experienced a really rapid rise in water. Now, this could well be a river that is in a city because it's rising so quickly because the water is flowing off the land very rapidly. Now, if you took the same river, same situation, but you had it in the countryside or you had it in an area with a forest, then we might see that the limb looks a lot more like this. And in this situation, we can see that the peak discharge is much, much lower. And in this situation, we can see that to be in flood, the river needs to be up here somewhere, because we can see that over here. And this river with the trees and the countryside here has remained not in flood because of the interception that's occurring. So this is why it's very important how we manage drainage basins to ensure that we don't experience flooding, and poor management, as in this situation, has led to a flood because there's not enough interception occurring, there's not enough surface storage. So, like I say, not something you're going to get a specific question on, you're not going to get a storm hydrograph presented to you in your exam, but it's a good way of visualising it, and it's something you can refer to, and it shows a good level of knowledge. So this is a simplified version of the diagram we were looking at. So to take a moment to describe and explain the impact that urbanisation has on the water cycle and water balance. So we looked at water balance previously. That was the equation where we had things like precipitation is equal to discharge and stream flow plus, not discharge and evapotranspiration plus or minus storage. Okay, so just have a go at describing the impact that urbanisation has. How has it changed the flows of water? So focusing largely on these orange arrows where it's changed the what's going on. So then we've got changes in the carbon cycle. So the impact urbanisation has on the carbon cycle. So you can have a sort of a little think there. What changes will urbanisation have for the carbon cycle? So primarily we're removing vegetation to build the city. So plants store a lot of carbon, and therefore by removing the vegetation we've lost the storage in the plants and the soil. And in temperate areas like the USA and Europe, the decrease in stored carbon is less significant in the tropical areas. So you've got to think, why is that? So why is it less significant? And the reason primarily is that there's an awful lot more carbon being stored in the tropical rainforest. It's a much denser biome. There's an awful lot more plants. So if you were to deforest an area of the tropical rainforest, a hectare of that, you've removed an awful lot more organic carbon than you have if you did that same thing in the UK. Also in urban areas we combust a lot of fossil fuels, and this increases the amount of CO2 up in the atmosphere. So urban areas account for 70% of the CO2 emissions that are being created from burning fossil fuels. So have a think and come up with a paragraph discussing this statement. So urbanisation in the Amazon is of greater global concern than urbanisation in the UK. So just a few ideas to jot down of whether you agree with that statement and why. So okay, so now looking at farming and how this affects the water and carbon cycles. So all of this ultimately is land use change. So humans have taken the natural pre-existing land use in this country that would largely be forest, and they've changed it to something like an urban area or a farm or something like that. So we need to think about ways in which farming can change the flows and stores of carbon and water. So have a look at these two questions. Again, you can pause, take a little bit of time. Okay, so farming compared to, say, a forest or existing cover is going to reduce the store of carbon in the soil and the biomass. So a crop has a lot less carbon in it than a wood. And after harvesting, there's only a small amount of organic matter that's then returned to the ground. The soil is exposed to the air, and this increases the amount of soil erosion. There'll be a lot less photosynthesis, and plants are only growing for a relatively short time, so 4 or 5 months. And then why are streams on farmland basically often higher than in natural ecosystems? So the main thing here is irrigation, so watering. We're watering the land, which means that there is already water in the pore spaces in the soil. So when it does then rain, we're going to get even higher flow rates. There's a lot less interception happening and a lot less transpiration because there's less plant life. Also, ploughing of the soil creates channels that water can flow along, and the use of machinery in the field compacts the ground, which then leads to increased surface flow. So we'll look at a little picture here. This is somebody ploughing. I feel this is probably something you're fairly familiar with in Norfolk, but we can see that it's creating these channels, and as you can see, this farmer has ploughed up and down the hill, and this creates channels that water can flow along, and that then removes soil organic matter. So one thing that farmers can do to try and help reduce this is if they were to plough across the hill in line with where the contours would be on a map, this then reduces the amount of soil loss, because the water would sort of flow into the furrow and then it would need to flow over into the next one and over into the next one, and often the water gets caught in the ploughed furrows, and it stops loss of soil and water to the same degree. So there's things that farmers can do to try and reduce the impact that they're having. Also needs to be aware that there's more than one type of farming, and this is where a lot of good evaluation can come from in a topic like this. Is much like with deforestation, it's not just one concept. So something like deforestation, you could deforest an enormous area permanently, or you could deforest a relatively small region and then leave it to regrow. And it's the same sort of situation with farming. So here on the left, we've got some hill farming, somewhere like Wales, and then on the right we've got arable farming somewhere like here in Norfolk. And the question is, which of these two is having a bigger effect on the water and carbon cycles? And the logic really is that the one on the left is having less of an effect, because if you look at that image, essentially the sheep aren't having a massive impact on that landscape. The area would look reasonably similar if it wasn't being farmed. There might be a bit more growth, but not significant really. It's unlikely that you would get something like a forest in that area or something like that. Whereas on the right here, this land has been very heavily changed to achieve what we can see with the combine harvesters. So the forest that was there before has been completely removed. The land may have been levelled. It's getting more compressed by the vehicles. And there's been an awful lot of change. So this sort of field on the right, in biodiversity terms, is thought of as effectively a desert. So there's only one thing growing, and it's really not very good for animals and plant life. And that's why we encourage things like farmers to have hedgerows, because that's very healthy for creatures like birds, and creates a lot more biodiversity. So anyway, hill farming is arguably better in terms of impact on the water and carbon cycle, but it's a far less productive process. So we can see in this picture we've got a few sheep, whereas in this picture on the right we've got a couple of combine harvesters producing huge amounts of grain that then becomes things like bread and pasta and other major staples of diet. So it's very much something you can evaluate in multiple ways, looking at the impact it has, but also looking at the productivity and all kinds of things like this. Okay, so this is a bit of a fill in the blanks about the impact that forestry has on the water and carbon cycles. There is a bit of information in the textbook here, page 120 and 121, about forestry. So the box you've got here on the orange background, this has got the terms that you need, and then you've got the blanks to fill it in, so you can have a go at doing that. Here on the blue background is the answers that go in the boxes. The one thing I'll just highlight is this term, rotational felling. What that means is essentially you take your area of woodland and you divide it into areas, like so, and then you would cut down a section each year. So you could well have, many sections in your forest, and the benefit of that is that you're cutting down a relatively small area, so there's still plenty of interception occurring. So if you chop down area 5, there's loads of interception still occurring in this region. There's still lots of carbon being stored, and animals are still able to sort of live within that woodland. So that's what's called rotational felling. The sort of opposing way of doing this is what's called clear felling, and you kind of come and you cut the whole lot down, and that's very destructive and very damaging. So this is a little bit more about the storm hydrographs that I showed you earlier. So we've got two different types. We've got type A here, which is what's sometimes referred to as flashy. So this is what you find when you've got an impermeable surface and you've got lots of surface runoff and very few trees. And then we've got B, which is subdued. And this is where we've got things like forests and farmland and things like that that's going to absorb a lot more water. So you want to use your notes to describe the characteristics of the drainage basins which would produce these two hydrographs. So basically explain how these two different curves would be created. So it's important to kind of appreciate that the different land uses we've looked at, they can form into a bit of a hierarchy. So arguably, say, natural forestry would be the best land use in terms of protecting the water and carbon cycles. And then next after that, we might have a sort of organic farming, quite natural farming, and then a more intensive farming, and then something like urbanization. And you can kind of see that as you gradually move through the different levels, we're getting less carbon being stored, and it's worse for the water cycle and things like this. So I want to put this into a bit of practice. So have a go at this question. Humans have a greater impact on the water cycle than the carbon cycle. Discuss. And you want to come up with a peel paragraph or two in which you discuss this. Okay. Okay, so the impact of water extraction on the water cycle. So this is where we remove water from rivers or the groundwater to use on farmland or to use in our homes and things like this. Okay, so first of all, we need to define these terms. Okay, so I'll give you time to do that. So if you want to pause and look up these terms, many of them will be in the glossary of the textbook, or you can look them up online. Okay, so looking at aquifers and what's called artesian basins, we'll have a look at these. So first of all, we were looking there at the definition. So we've got the water table here. So this is the water table. So below this point, the ground is saturated, full of water, and above this point it is dry. So if you were sort of digging through this, then the brown section you would find that the ground was basically dry, and then as you got down to the water table, your hole would start to sort of fill up with water. So if you want to drill a well in this area, you'd have to drill all the way down, so dig your well all the way into the aquifer, and then you can lower the bucket into the aquifer down here and collect water. So above the dotted line, you would your well would have no water, and where the dotted line is where the water level would be in the well. Okay, and this affects the river. So if the water table drops, then the river drops, and if the water table rises, the river rises, basically. Okay, and then we've got an aquifer is an area of ground that contains water. All right, and that's where you will find the groundwater when you're trying to drill a well or something like that. So this is a bit of an example. This is the London area, and this also helps to explain one of the other terms that's possibly a little bit less easy to make sense of. So what we're looking at is chalk is a permeable rock, meaning water can be held in it, whereas clay, which the rest of this is not permeable. So what you have is water in the layer of chalk, trapped in the layer of chalk, and the water cannot escape into either the firestone or into the clay. So this creates a perfect aquifer. It stores the water, and the water is confined within it. Now, in the definitions, we have the term potentiometric surface. That's the height the water would rise to potentially if it wasn't prevented by an impermeable rock. So in this example, we've got different water heights. We've got this lowercase a. So the potentiometric surface for A would essentially be up here. Okay. So if the water wasn't being confined by the clay, the water would be able to rise to that height. Okay. So what we want to do for this task is, for this diagram, is figure out which of the boreholes, which are represented by the capital letters, would contain water. Which ones would be water filled, which ones would be dry, and which ones would be what's called artesian. So artesian is where water rises to the surface under its own pressure. Okay, so in this situation, level A, the water, let's try to draw this in a reasonably straight line. The potentiometric surface is really high. What that basically means, to kind of give you a bit of a clue here, is that all of the boreholes will be artesian because the potentiometric surface is above the surface level of the borehole, meaning the water wants to rise higher than the surface. Okay, but then if we look at B, we can see that some of the boreholes, the water level at B will be within the borehole, and some of them, the water level will be above the borehole. So for B, for example, borehole C here would be artesian because it's so low lying and the surface is so low that the water level is above it, whereas something like borehole B is going to have water in the borehole, but it's not going to rise to the surface of its own accord. It's just you're going to look in the borehole and be able to see the water there. Now, if we take level C where it's lowest, some of the boreholes aren't going to have any water in them at all. So some of the boreholes don't reach level C, and some of them will have water in them, but with level C, none of them will be artesian. So to get an artesian well, an artesian borehole, the potentiometric surface needs to be above the level of the surface where the borehole reaches the surface. Okay, so it's a bit of a challenging concept, and it is covered in the textbook. So if you want to sort of have a bit of a read about this is page 123, will help a little bit with understanding that concept. So this graph shows water abstraction versus water level. This is in the London area. So we've got the years here, so going back to 1820 all the way up to just after the millennium. So back in 1820 we basically weren't extracting any water at all, and the water level was essentially very high. And then we started doing all this extraction to a peak of extraction around the 1950s, and then for various reasons it started to drop. So primarily there's a lot less industry in London than there was previously. A lot of the industry has moved out of the city, so we're extracting a lot less water. So you can see the water level dropped and dropped and dropped and dropped, and then when we stopped extracting water it started to rise again. Now this created a bit of a problem in that between sort of the time that the water had dropped in the Victorian era to the present, in London we had built the tube network. So as this water began to rise, it started to flood some of the tube lines. So then what's happened is they've started to extract water again just to try and keep the water level low. So that's one of the reasons why we might extract water, just to try and kind of protect against flooding, keep the groundwater level artificially lower than it should be, to try and stop towns and places flooding, particularly if they have underground structures and things like that. Okay, so we've got a few notes to take. So pages 122 and 123. So there's a mini example here, a place called the River Kennet, and we want to look at the impacts that water extraction has on the stores and flows of the water cycle. So there are some figures on page 122. So by figures I mean like actual data, things like percentage and years and things like that, which are very useful to have. And then if you take some notes on the aquifers and artesian basins section on page 122, 123, to really help understand what's happening in these diagrams, okay?